Hi there, Manuel here. Welcome to part 6 of the particles course. Today we want to deal with a classic in particle simulation, a twister effect, a hurricane, tornado. So we want to use one of the inbuilt forces, the curve force, to create this twister effect. It's a very straightforward setup, so let's directly dive in. I already prepared this start scene for you, and it includes a particle object, and inside you will find a curve node. I suggest that you use this curve node, although you can of course draw your own, but if you use this, you get the exactly same effect as I will. So, this is just a polygonal curve, so it just has a few points. To make it smooth, append a resample. This will create more points, and if we treat polygons as from straight edges to subdivision curves, we get this smooth curve. And we want to use this curve to drive the particles. So we want to create a force along this curve that we can use to create our twister. But before we can start to do so, we need some particles. So lay down a grid to scatter some particles on. And the grid is 5 by 5 units this time, like so. And now append a scatter to create some points. And for now, let's scatter 10,000 points. Because eventually I want to make the tornado move through this field of particles and suck these particles in. That's why I'm creating this field of particles. And for this effect we don't need this even distribution, so turn relax iterations off. Now that we have some particles on the ground, let's append a popnet. Standard popnet appended here. Wire these points into the first input and dive inside. And inside we find this predefined source first input, and we want to use it to replicate these points as particles, so switch from scatter onto surfaces to all points. And maybe let's rename this to source A, because later on we will have more sources. Turn off the guide, and at the moment it's creating particles all the time. We want to stop that. We only want to create particles in frame 1. So go to the burst tab here and type an expression $f is smaller than 2, which will evaluate to 1 only in frame 1. So now we are creating particles once. And now we can, in theory, lay down a curve force. So pop curve force. This is our curve force appended here beneath this source A. The curve force is looking for a curve to drive the force. And you have different possibilities here. You can use context geometry. In my case, I want to just point to a sub. But before we do that, let's append a null to our curve. And let's call this null out curve, or uppercase. That makes it easier to pick it, and if we want to change the curve, we still can refer to this object here. So now that we have that, just pick this out curve here. And as soon as you do that, you immediately get this visualization in the viewport, these red lines. And that is our curve plus the search radius around the curve that the pop force uses. So the pop force is active inside of this red region here. And if we now press play, you see that these particles get sucked up and move along the curve, even with the standard settings. But that is not exactly what we want. We don't want all the particles that are inside of this radius to be sucked up immediately. Instead, we only want a little small circle here in the middle to become active and then move along the curve. We could go in and change this maximum influence radius. That makes the radius of the force smaller. But eventually the particles can leave the force field very easily if it is so small. So we want a big force field, but we only want few particles to get active and move through this force field. To achieve this, we have to do something else. We have to create a helper object that moves some of the particles to a different stream, and then we attach this pop curve force to this second stream. To achieve this, let's go one level up, and let's create our helper object. I plan to attach a sphere to the very first point of this curve. If I turn on point visualization, you see that this is point 0, and here is where I want to have a little sphere. So let's append a blast to our curve, switch it to points and blast point 0, and then tick delete non-selected, which will just leave you with point 0. And now we can create a sphere. Let's make it radius 0.5, and let's use a copy to points to copy this sphere to this one point. Now we have a sphere here sitting at the very first point of our curve. And again, let's create a null to have a node to refer to all the time, and let's call it outActivate, because this is the object we want to use inside of our popnet to activate the particles to switch streams. So with this in place, let's turn off this visualization. Let's dive into the popnet again. To create a different stream, just lay down a stream pop or a pop stream. And don't be worried that we don't attach this pop stream to the source A. Particles do not exactly work like SOPs, so the pop stream does not need an input to know which particles to move to a different stream. This is more or less like a wrangle or a pop warp. It always acts on all the particles, although it is not connected. So this input here is just the reference stream, and we don't have to connect it. What we want to achieve is that all the particles that are inside of this little sphere are added to this second stream. So, under rule, let's deactivate the rule completely, otherwise everything will be in the new stream. Instead, go to bounding, enable the bounding, and go to bounding object. And that makes this SOP field available that lets me pick an object, and in my case I pick outActivate. Now, all the particles that are inside of this pop activate will switch to this pop stream 1. So let's connect the pop stream to this wire pops into here, otherwise it does not get executed. And to see if it works, let's lay down a color, a pop color, and let's put it here. And you see, as soon as I do that, everything turns white because all the particles don't have a color attribute and it defaults to white. And here inside of this blue sphere, we have lavender particles. And that means the pop stream is working. So now if we revisit our curve force and up the radius to 3.5 or something big, and then detach it here and instead move it over here, and if we now press play, you see that only the particles that are inside of this blue sphere get active and are moved by the pop force. And that means we can make the force field itself very big, although the particles that are affected are coming from this very small region here. Exactly what we want. Because now the curve force is only executed on the particles coming from pop stream 1. And if you wonder why this is, well, in reality, a pop stream is nothing but a group, an automatic group. And inside of this pop curve force, let's quickly go to allow editing of content and dive inside. You will find this geometry warp here, which is the curve force, the actual curve force. And if you go to data bindings, you see this group here has an expression, and the expression is called op stream name. And that is a special expression that is created for particles that automatically evaluates to the active stream. So in our case, this is stream pop stream 1. And that is how all this stream system is made to work. It is just groups, but this pop stream expression always knows which stream or which stream group is currently active. And that's why this pop curve force is only executing on these particles and not on these particles here. So it is working, or is it? Let's play it again. And yes, the particles get a force, but look what happens. Maybe let's get rid of this pop color to see it better. These particles are flying outwards in a straight line. Seems as if the curve force only acts the very first frame on them, and that is the case actually, more or less. And that is because of the pop stream reverting to default as soon as the particles are leaving the sphere. To prevent this behavior, we have to tick preserve stream. That means once the particles are in the stream, they stay in the stream. So if I tick this, now the particles are actually following the curve, because now the curve is acting on the particles all the time. Okay, this is cool, but it is only very few particles that are moved upwards, because we only have few particles here on the ground. And we could scatter more particles, but that gets very heavy, because then we have a lot of particles here on the outer rim that are not moved. So instead, what if we just cheat a little and create a second emitter that is emitting particles just where we need them, here in the middle. So to do this, let's go up one level again. And let's create a circle this time to be used as an emitter. Let's switch this to be lying on the ZX plane, and let's make it a lot smaller, 0.1 say, tiny little circle. Other than that, let's use exactly the same technique as before, just duplicate the copy to points, but this time duplicate the circle to the first point. So here's our sphere, here's our circle sitting at the first point. And now let's duplicate this null, and let's call it out emit B, like so. With this in place, dive back into our popnet and let's create a second emission. Lay down a pop source, and let's call this one source B, like so. And let's wire this in. And now go to this merge, and just for clarity, move this source B one level up, such that the order is correct again. And now we want to use a SOP, an external SOP, to be used as a source. So let's go and pick out emit B here. And this immediately creates particles, because this is set to scatter on surfaces, and we can leave it like that, but I prefer to go up and introduce a scatter here after the copy to points, but before this out node, which will create points on my circle. Turn off relax iterations, and for now let's scatter 500 particles. And don't forget to vary these particles per frame, because at the moment they are scattered at the exact same position in every frame. So let's put an expression here in the global seed, say $FF for floating frame. And now we get different locations in every frame. Very good. And if we now go to the popnet again, we have these particles being created here. But now that we have points coming in, we have to switch to all points. Let's turn off the guide, and if we now press play, you'll see that we have an emitter that is creating a lot of particles, and they are flying upwards. The problem is that we get this weird banding here, and that is because all the particles are created in one frame and then they are moved per frame. We don't have substepping in this particle simulation, so we get this banding effect. And to make it less noticeable, we can do one thing. We can go to birth here, and here we have a setting for jitter burst time, which is set to positive, and what that does is it gives the particles a random burst time. And that means they are moved a little bit even in frame 1, so they don't start all exactly here at the location where they started. The problem with this is that these particles don't have an initial velocity, so they don't move. So instead of using positive, let's put this to negative, which will give our particles negative burst times, and that means they now have enough time to pick up the force that we applied. And if we now press play, the banding is still visible, but less obvious than before. And later on, we will vary the particle attributes on the curve force to make this banding effect vanish entirely. But for now, keep it like this. So now we have particles that are moving from the particles here on the floor, and we have particles that are emitted, and all of them are moving upwards along the curve. Time to have a look at our curve force. The curve force is a mixture of different forces. It creates 3 individual forces and mixes them together. And these forces are the follow force, the suction force, and the orbit force. The follow force is straightforward. That is just the force along the curve. Internally, it's creating a normal vector that is pointing along the curve, and then it's sampling this in the proximity of the particle, and it is moving the particles along the curve. The orbit means that it is creating a force that is orbiting around the curve. And this orbiting behavior leads to particles flying away from the curve. And to counteract this, you can dial in a little bit of suction force. And the suction force is just a force pointing from the particle to the curve. So with these three values, you can define the behavior of the curve force. And then you have this force value here, the inherit velocity scale, and that is just there to inherit the velocity from the curve if it is animated. In our case, it is not, it is static, so it will not inherit any velocity because the curve does not have any velocity. So, for example, at the moment they are moving upwards. All three forces are in place. If we just go up with the follow scale, they are very fast regarding traveling along the curve, and that makes them thinner overall. So by changing these values, we can specify how the curve force should work. But there's another thing. With Houdini 13, side effects introduced pops inside of DOPs, and with this change, they introduced the concept of wind. Wind is an internal concept of the solver, so the integrator is using it, and it is there to deal with the problem that forces add up and get stronger and stronger over time, and things can explode. And what wind does is it caps the maximum speed, basically. So it moves the particles or accelerates the particles until the air resistance tells them to not move faster. That is a nice concept, but the problem is that the target velocity, so the target speed they have, is just computed from the forces. So if you have very large forces, this velocity is larger, and if you have small forces, the velocity is smaller. And that is not what we want in our case. So we want to deactivate treeless wind. Now we are back to the old pops, so to speak, and we are just using forces. If we rewind and press play, you see that now everything is just shooting outwards because the forces are very strong. And to counteract this, we want to introduce a pop drag. So if you have a look at the pop drag, you see that the pop drag has wind parameters too, and in reality it is using this wind system. The difference being that this wind velocity is set to 0. So the pop drag is trying to slow the particles down to eventually reach 0. Instead, the wind here in the pop curve force will try to match the target velocity computed from these forces. That is not what we want. So instead, just append the pop drag here and see what that gives. And now it is very nicely following the curve because the pop drag is slowing the particles down, but the forces are added in each and every frame and counteract this pop drag. So that is pretty much like the old pops with a drag. It's worth to mention that the pop drag is quadratic, not linear anymore. So now that we have this, let's try with values, say 10 for follow scale, but we want to give them a little orbit, so put a 10 in orbit too. Now they are orbiting, and due to this orbit, they are creating a much thicker particle cloud here. To counteract this, increase the suction force to say 7. And let's see what that gives. And that is quite nice. So now they are orbiting around the curve, they are moving along the curve, and they are sucked in. But that is not all that we have to adjust to make it work. Because here, down here, you find these tabs called fall-off. And they are using these spline curves here, these spline ramps, to modify these force values even more. This ramp modifies this value or multiplies it with respect to the distance of a particle to the curve. So this here on the left is on the curve directly, and this is on the outer radius. So for the force follow, the force is very strong in the center and then gets weaker and weaker and weaker until it drops off to 0 on the outer bounds. We don't want that. So take this point here on the right and just move it up such that this force is always 10 and does not fall off. With the suction force, the fall off is exactly the opposite. The suction force is not present in the middle, so there they are not sucked in, but the further they get away from the central curve, the stronger the suction force will be. Again, this is not what we want, so let's move this point up, like so, to create a constant suction force. And then for the orbit, again, the default tells the force to drop off, but we don't want that. And then we have the velocity, and we even want the velocity to be constant. So, although these ramps are giving you a lot of control, in our case we don't want that. Let's see what that gives, and that gives a very nice twisting behavior. You have under global forces a combined fall-off, where you can dial down all the forces with respect to the distance from the curve, and then you have this ramp here that scales the forces along the curve. So not with the distance, but along the curve. And that is something that we want to use. At the moment, the curve is 100%, and then it drops off here at the end of the curve. And by removing this knot, we just want to make the force get weaker and weaker and weaker until it reaches the end of the curve. So let's see what it gives. So the particles are slowing down a little bit. Very nice. And then you have the shaping, and with the shaping you could, in theory, just vary this radius here. But for our setup that is not necessary, because we want to keep the force field large to make the particles stay inside. So now we have the basic effect in place. We have a twister, but it does not look too interesting. So to make this boring twister into an interesting twister, it is about variation. We have to vary the attributes. And we want to start by varying the curve force a little bit. And if we go back to individual forces, at the moment the forces are set for all the particles, but we can change that if we tick use expressions. Expressions enable you to write a little snippet of VEX code to vary the values for individual particles. The easiest way to use it is to go to this little menu here and say pass through, and then it will fill in all the variables that this code field here knows of. And that is the 4 forces. So if you hover over one of these parameters, you see that the internal name is, in this case, scale follow. And this little code snippet knows this internal name. So if you set something to scale follow, it will override this value. But we don't want to override values, instead we want to vary values. And we can do this by not just setting them, but by multiplying them. So let's vary this suction scale. So let's get rid of scale suction is scale suction, which does not change anything. And instead, let's put an expression here. We want to apply a random value, so rand. And then we can use add_id, because the ID is different for every particle as a seed. And let's add something to this ID 1, 2, 3, 4, 5, say. And that is our random value, like so. Let's see what this creates. And you see now the particle cloud is a lot larger again, and everything is more fuzzy because each and every particle has now a different value for the scale suction. But the random function returns values between 0 and 1. That means all the particles have values between 0 and 1 for the suction scale here. That is not good. Instead, we can say times equals. So now this value between 0 and 1 will be multiplied by whatever you have here in the parameter. So now the values will vary between 0 and 7, which is better. But it is not perfect either, because we only want to vary the values around the value of 7. So put the entire rand function into a fit function, because then we can exactly tell what the values should be. And we want to fit this between, so the input range is 0 to 1, 0, 1, that is what the rand returns, and we want to fit it to 0.8, say, and 1.2. So a little less and a little more than 7. So let's see what this gives. Rewind and play. And now we are back to our twister. It looks a little bit more fuzzy now. That is nice. The next thing that is not perfect is that the emitter is emitting the particles at a constant rate, and that means we have always the same density of particles here on our twister. Let's vary this, but we have to vary this one level up. So go up one level, and we can vary how many particles are created here on the scatter node. At the moment we are creating 500 particles, so let's replace this number by an expression. And we want the rate to go up and then down again and then up again, and that can be modeled by a sine function. So let's type sine of, say, $floating frame times 20, say, like so. This is an H script expression, so we don't need a semicolon. And let's see. And you see, you have no particles. Do you see that? And then you have some particles. And that is because the sine is returning values between -1 and 1. And we only want positive values, so let's add 1 to this. So it's now only positive. We have always particles. And now let's take all of this and let's increase the number by multiplying, say, 800. No, not a plus, but a times symbol. And now you see it's pulsing. We have few particles and then a lot of particles. By making the popnet visible, let's check if this looks more interesting. And it does, because now we have varying density on our twister. But still, it is not too interesting. And we can change this while we are here on geometry level by animating our curve. So what if the curve would move around instead of just being static? And we can do this. So let's try it out by applying a transform node right after the resample. And we want the curve to move around. And we can do this by keyframing it, but we can do it too if we use an expression. So in the translate for x, let's write an expression. And I want to use a noise. But a noise needs an input. And as an input, I can use the centroid of the incoming geometry, for example. And that is a local variable called CEX, because that is the x component. And let's add an arbitrary value to it. Let's say 7 to vary it. And then we want to make it time dependent. We want this to change over time to get an animation effect. So let's say $f divided by 60, like so. But this won't work because the noise needs 3 input values. So inside of the function we have to say comma $CEY, which is a y component, and $CEZ, which is the z component of the centroid. So this is giving us a noise that is varying in the x component only. Oh, and I forgot to close the parenthesis here, which is nice. Let's see what happens if we press play now. And our curve is moving a little bit left to right on the x-axis. Let's make this movement a little bit more exaggerated by multiplying 2.5 on top of all of this. And now the curve is moving. And to make it even more interesting, let's replicate this by copying the entire expression and putting it here in the z component. And because we want a different behavior for the z component, let's switch this 7 with the 0. Then we are sampling a different location in the noise field and we are getting different values. So let's see. And now our curve is moving around. Let's check what this changes with our particle system. Oh, and it changes a lot. A, we are now eating more particles from the ground, and B, the behavior is a lot more interesting because the curve is now moving. And that means the forces are varying more and the behavior gets more interesting. But we don't want to stop here. The curve is moving now, but the curve shape is not changing. And with a real effect, the shape should change. So why don't we just use more noise to not only move the curve around, but change its shape? And we can do this here after the transform. What if we just append a point warp? Point warp. And let's append it here and let's call it noise deform. Noise deform. And make it visible. Dive inside. So let's use some noise to deform our curve. For that we first create an anti-alias noise node and connect its sample position to P. And this is generating noise, but we want to generate 3D noise. So switch the signature from 3D input 1D noise to 3D noise. Now this port changes color because now it's a vector. And what we can do now is we can add this random or this noise vector to the position, like so, and then we connect this to P, and this gives a noisy curve. If we press play, the curve is noising around. But we don't want to apply the noise in all directions, we only want to apply the noise in the XZ plane. So a little trick, use a vector to float. Vector to float, to convert this noise vector into 3 float values, and then a float to vector to recombine these values into a vector, but only connect x and z. That means y will be 0. And now let's add this here to our points, and now we get deformation only in the XZ plane. But the noise is too small, so let's go to the noise and change the 3D frequency of the noise to say 0.34 on all components, like so, and that gives less of a noise. And maybe let's increase the amplitude to 5, like so, and let's go down with the roughness. And now we have very smooth animation here on the shape of our curve. And to animate it even more, we could promote the offset to move the noise field. And one level up, we now have an offset parameter. And we could, for example, put an expression like $f divided by 100 here into the x field of the offset, which will make the animation even stronger because now the entire noise field is moved around. So very nice. Now we have a curve that moves in x and z and that changes shape at the same time. So let's see what that gives. Make the popnet visible and press play. And now it starts to be a lot more interesting. Look at these nice shapes that are evolving now. Because now the forces are changing all the time because the shape of the curve is changing. And that really gives a lot more interesting behavior. I like the effect, but I would like to vary it even more. Especially the individual forces per particle. But I don't want to do this randomly. I want it in a little bit more clumpy fashion, so little patches of particles should have the same values. So why don't we just add an attribute to the points that generate the particle, then we have values that we can use to vary the properties even more. So this scatter here is creating the points. And after the scatter, let's introduce another point warp. Point warp. Put it here and call it create noise too, because that's what I intend to do. dive inside. And this node will look quite similar to the one we just created. So lay down an anti-alias noise and connect it to P. And remember that the anti-alias noise is outputting values roughly in the range between minus 0.5 to 0.5. So let's fit these values from minus 0.5 to 0.5, and the output range should be 0 to 1, because now we can wire them through a ramp parameter. Call this ramp parameter ramp noise and switch it from color ramp to spline ramp, because we are dealing with a float here. And now let's, for debugging purposes, connect this to CD. Not much changes, and that is because this circle here is very tiny and the noise field is very large. So increase the frequency of this noise by a good bit. And now let's up the value here of this ramp, and now we can use the ramp to exactly dial in the noise pattern we are after. So now that is what I was looking for. I have little clumps of white particles and little clumps of black particles. But to use it inside of the popnet, it's not that nice to use CD because it is a vector. Instead, let's bind export a new attribute, and let's call this attribute noise. Noise, like that. So now we have a noise value that we could use inside of the popnet. So make the popnet visible and dive inside and revisit our pop curve force. And here inside of the expressions, we now can use this noise value. So if you middle click here on the node, you see that we now have a noise value coming in from outside. And we can use it here. But before we use it, we want to fit it. Remember, we are now outputting values between 0 and 1, which is a little extreme. So let's create a variable. Float NSE for noise should be fit the incoming noise attribute, that is between 0 and 1, so 0, 1 input range, and the output range should be 0.9, 1.1. That has a weaker effect. So now we have a noise value that is fitted, and we can use it to make all of this a little bit more interesting. So I'd say, why don't we move all of this random business here from the suction force, where it only has a very little effect, to the scale follow. So copy all of this, copy, and put it here to vary the scale follow. And don't forget to multiply with the scale follow like this. And let's see what we have. Oh, and now everything is a lot faster. And now let's use the noise instead for the scale suction. So replace all the fits business here with NSE, the value we computed. What does this give? Okay, now it's looking very interesting. But maybe we can just vary all this business even more by just multiplying NSE on top of it, like so. And this looks nice. This looks really very interesting, because now all the particles have different values for suction and for follow, which is nice. For now, go to the guide and turn on show curve only. That is less distracting. Rewind and play. Now it's really starting to look nice. So maybe let's vary things even more by applying a little bit of curl noise force. And we can do this by introducing a pop force. And let's put it here after the curve force, but before the pop drag. And let's say the amplitude should be 2. And let's keep the rest to default. Let's see what that does. And now it is applying a little bit of curl noise on top of the entire simulation. And that makes everything a lot more interesting and a lot more varied. Now you get these little things here. And at the top of the curve, the curl noise really starts to show, because there the forces from the curve force are fading out, because we set that. And if you ask me, this is a nice twister effect. I would say, let's wrap it up, call it a day. That is how you create a nice twister. So what you hopefully get from this tutorial is that it is not always the very complicated setups. We are in principle only using the curve force here, but it is about variation. Nature is very varied. In nature, no two particles would behave exactly the same. And if you want to create interesting, natural-looking effects, it is about putting variance wherever you can. So don't go with randomness, but try to vary things. And this will give you something that is visually compelling and interesting to look at, like this twister effect here, which always changes shape and does interesting things. Oh, and by the way, because we use this noise value to vary the attributes, we get some nice shading for free, because now we have all the black particles on the outside of the twister and the white particles on the inside. That is probably because we set this noise value as a suction force, and that can be used for shading too. So, with my example where I rendered it, I used this color value directly in the shader. So I hope you had fun with this tutorial, creating this twister effect, and there's of course room for playing around with the values and varying even more things on the curve. But that is up to you. Let me see what you are coming up with, and stay tuned for the next part of the Particles course. Thanks, and goodbye.